So the question was, what's the best way to memorize all these reactions? And there's a few, right? A few dozen reactions to know. First, I think if you're going to be able to remember the reactions, you need to recognize what changes it's causing in the molecule. And to be able to identify the change it's causing in the molecule, you need to know your functional groups. If you don't know your functional groups, full stop, you can't memorize these. It just won't work. Um, if you know your functional groups, it becomes a lot easier to memorize the reactions. Or again, memorize versus familiarize. If you're memorizing, oftentimes you've got a flashcard and it's just the same thing over and over. If you're familiarizing, you're changing the carbon backbone, you're changing the structure, but you're doing the same reaction over and over. So familiarization beats memorization. Familiarization is harder to do because how do you find access to all of those different molecules to practice on? Active has practice problems. Canvas has my old materials. So you've got practice problems there. So familiarize, but if you're going to memorize anything, memorize the names of the functional groups. And to an extent, that means you have to memorize some names that aren't explicitly written as functional groups, like this is a vicinal halohydrin. I don't actually have the halohydrin listed on your table of functional groups. But this is a common product if you're doing an alkene addition reaction. So being able to at least name the functional groups and especially their regio relationship, or a vicinal halo ether helps you remember what's happening a lot more. And for a lot of the reactions, if you know what change is happening in the functional groups, the reagent makes sense. Like the reagent here has chlorine and an alcohol, bromine and water, or you've got hydrogen, or you've got strong oxygen containing compounds, oxidizers that are going to do some oxidation and create carbonyls or something like that. So know your functional groups for sure. I think you all saw my message, but an update tomorrow night from 6 to 8 p.m. in SI 354, which is right up there. Actually, yeah, yeah, it's right up there. I think it's a smaller space. Um, this building, but third floor in the other wing from our classroom. They'll hold a review session, especially for you guys. So take advantage of it if you can. If you can't take advantage of that, try to go tonight, right after class, and go spend some time with Johnny in the tutoring center. Anything that you guys want to add to it before we just dive back into more problems? Okay. Um, I don't think that I finished answering all of the questions that were on the exam, so I want to start there first. In the 2 days since I saw you guys last, has anyone taken advantage of the final exam archive module? Not yet. You looked at it and you cried? Do you guys remember whose question was 34? Hamza, was this yours? There's a typo on this. And I think I addressed the typo in the answer key. And I wonder if the typo is part of your question. So let me address the typo first. And if it's not the question you have, then you can ask your question. Okay. The typo is in the Diels-Alder reaction. the pi bonds are not shown correctly. It starts with a diene and a dienophile, and it should form a cyclohexene structure, but instead it forms a cyclohexadiene structure. So the two pi bonds you see in the final product should not be there, and instead there should be a pi bond just between carbons 2 and 3 of the Diels-Alder. What was your question on question 34? This should feel a little bit like the question you had on the midterm, where I gave you a mechanism you had never seen before. I gave you the change in bonds, and I simply asked for adding arrows to draw it, to show that. And after the midterm, we worked on stuff exactly like that. We talked about how to spot the difference, right? What bonds are breaking, what bonds are forming, and how do I need to add arrows to highlight that? So let's say that we're working with the structure on the left. We're going to solve the mercuronium problem. Again, not a mechanism that I asked you guys to know, but a mechanism that I told you if you mastered the reactions I asked you to master, you would be able to understand any of the other mechanisms. And that goes for this. This mechanism is nearly identical to the halogenation mechanism, except that it's not a halogen. Um, look at things that break. I need to break the carbon-carbon pi bond. So I need to have an electron arrow that starts from the carbon-carbon pi bond. Where are those electrons going to go? Maybe I'm not sure yet. But I know I need to break it. Other things I need to break. I need to break a bond between mercury and this acetate group. So how am I going to break it? Will the bond break to mercury or will it break to acetate? Well, we can actually see that the oxygen becomes negatively charged. That's given to us. So the oxygen must be taking the electrons. Bond breaks to the oxygen. You guys might remember that earlier in the semester, I told you that when bonds break, they break toward the more electronegative atom. And you may not know the electronegativity of mercury, but hopefully you know that oxygen is the second most electronegative atom on the periodic table. So I doubt mercury is more electronegative than oxygen. Bonds break toward the oxygen in this case. Then think about bonds I need to form. I need to form a bond between mercury and carbon, and I need to form a bond between mercury and carbon. This also shows you lone pairs. It shows you that mercury starts with two lone pairs, and it shows you that mercury ends with one lone pair. So I need to have an arrow that starts from one of mercury's lone pairs and points somewhere. So I need this bond to break, and I need to form a bond to mercury. Let's have this bond attack mercury. I need this lone pair to be used, and I need to form a bond to carbon. So let's use this lone pair to form a bond to carbon. Think about the bonds that break, think about the bonds that form, and think about how your arrows can be used to showcase them. Yeah? Now, in the case of the question on the right, it's impossible because I messed up. And with that typo is a bit like that sucks. Anybody that solved that one, I had to grade extremely generously because it just made no sense. But don't worry, I've already made sure that next week's exam doesn't have silly little typos like that. And I'll try to make sure again, because there's going to be one that slips by me somewhere, unfortunately. Did that answer your question? Okay. So I'm not going to show the one on the right because it just doesn't work. But It would be a very similar process to this. Okay, Vivi, no follow-up on this? Anybody else follow up on mechanisms, especially mechanisms you haven't seen? Do you feel like that's fair? You did it on the midterm. Why not do it on the final? Allie. Sure. So let me fix this example. Sure. You guys are all right if I erase this. Also, compared to the halogenation, exact same number of steps or arrows. Alkene attacks a halogen and the halogen attacks back and kicks off a halogen. The only difference is that it's not a halogen and it's mercury. Okay, so let me fix the product, show you what it should have been. We take our conjugated diene and we take our dienophile. We should make a six-membered ring. That's why it's called 4+2 cycloaddition. But the pi bond, the number of pi bonds should go from 3 total to 1 total. And the pi bond that shows up should be located between atoms 2 and 3. So, and we did a problem like this earlier in the semester when we were learning spot the difference techniques. What bonds break, what bonds form. 3 to 4 pi bond breaks, and a 4 to 5 bond forms. 1 to 2 bond breaks, and a 1 to 6 bond forms. 5 to 6 bond breaks, 2 to 3 bond forms. There is more than one way to have your arrows move. And in this reaction, there is a best way, but it's not one that I would grade on for this question because this question is testing on, can you show the arrows needed? And this one lost all its rights anyways. This cyano group is pulling electron density towards itself, which means the further out from the electron withdrawing group, the more positive. So how my arrows should actually move is that they should attack further away from the electron withdrawing group. Sometimes there's electron withdrawing groups on both carbons, in which case it wouldn't matter which way it flows. So for the 3 to 4 bond breaks, remember that electrons held between two atoms can be broken, but they're retained by one of those two atoms. So when the 3 to 4 bond breaks, I can either show it forming the 2 to 3 pi bond. That would mean carbon 3 gets to keep them. Or I can show it forming the 4 to 5 sigma bond, because then 4 is keeping them. But in no way should I suggest that these electrons can go to somewhere else in the molecule or another molecule and no longer be held onto by either atoms 3 or atoms 4. They can get pushed to one side or the other, but they have to stay in that general vicinity. So I'm going to show atom 4 attacking atom 5. That breaks the octet at atom 5. So 5 needs to lose some electrons. 6 takes the electrons from 5 and attacks atom 1. That breaks the octet at atom 1, so it needs to lose electrons. So 2 takes the pi bond and shares it with atom 3, which already lost electrons because 4 took them. Kirsten.
You said the best way to do this. Is the best way either going that counterclockwise or going clockwise? Both of them are the best way.
No.
Specifically going counterclockwise is that.
Yeah, in this molecule, specifically going counterclockwise is the best way. And it's because of this resonance form that puts a positive charge onto that carbon number 5. So the electron withdrawing group, this nitrile or the carbonyl, we saw examples where there are carbonyls attached here. pulls electron density towards itself, which creates a better partial positive on atom 5, making it more likely to be attacked. So I would say in this molecule, counterclockwise is a better mechanism, a better explanation of how electrons are going to flow, as opposed to having these arrows go clockwise. But if this had been drawn correctly, I would have graded the same for either direction. But I like to showcase that there is a best way, a logical reason why electrons might flow one direction over the other.
We do both of them. You get one right, one wrong.
Oh, okay. What do you guys think about that? There's a lot of questions here where you have the choice between mechanisms. I do that in OChem 2 as well, and in OChem 2, I have my students solve multi-step syntheses, but they get to choose between one or the other. I had an OChem 2 professor that said, choose one or the other, and if you don't circle one, I will grade A, no matter what. If you solve both and you don't tell me which one to grade, I'm not going to decide and I'm not going to grade both. I'm just going to grade A. What do you think? What should I do? I have my answer, but I am curious. You guys are the ones that would be impacted by my grading practice. What do you think is a fair practice? Correct both? Do the one that has the least errors. So grade both and then award the highest points, as if you're doing 2 attempts at a part B and I'm giving you the highest score. Yeah? That's what you think is the fairest to me and you? Because you can see I don't say anywhere in the instructions, if you don't tell me which one to grade, I will just grade this or that. And that's because my policy is I do grade both of them. But would it be a fair policy to grade both of them and then take all of the points you lost from both and sum them? Like this is a 3-point problem on the bottom, the one that Hamza brought up. If you got both of them wrong and you lost all 3 points, can I take 6 points off?
You're just giving something.
Do you get bonus points for getting them both right? If I wanted to cover my own butt, I would say circle the one you want graded, or I will grade only A. But I don't care that much to cover my own butt. And if you put the answer to both of them, my interest in this job is seeing how well you understand stuff. So I am curious to see how well you did. If you solve both of them, I'm going to look at both of them anyways. And to be honest, I can grade these at a glance, right? Like you're adding 3 arrows. I know immediately whether you have the 3 arrows correct or not. If I handed it back to you and asked you to grade it, you're learning this stuff. I would expect it takes you a bit of time to reason whether the arrows are right. But for me, it would be fast to grade. So I grade both. And then I give you the score for the one that has the least points lost. But, you know, I want you to feel confident in one or the other, and I would love to see you tell me which one. I think I actually used to say circle one or the other. And now I just say choose, which is vague. You can choose it without circling it, right? Okay. That answer your question on the mechanism? Okay. I think that was all that we had from the final exam. So I want to fix the alkyne reactions. This is what um, this is what we had on the worksheet. Let me pull up the worksheet so that you can see what I'm talking about. Was it? It was Unit 5. Hmm, where does it do that? Okay, um, we've got these 5 reactions. Do you guys recall why I separated these diagrams the way that I did based on regiochemistry? I wanted to highlight reactions that were regiospecific and reactions that were not regiospecific because that is an important aspect here. What I messed up on though, so going to the top, oxidative cleavage. Oh, oh, yeah, I screwed up there. I think I caught that in the moment and I told you to fix it. It shows it wrong, but the oxidative cleavage of this terminal alkyne, yeah, gives you a carboxylic acid. And if it's a terminal alkyne, it also gives you a dicarboxylic acid, which is carbonic acid, which decomposes. On the left, I wanted to show uh, HX addition. One equivalence versus excess, or in other words, two equivalences. That's a regio-specific reaction. It's Markovnikov addition. And I wanted to show that on the terminal alkyne because on an internal alkyne, you don't see the difference between one carbon or the other. And then on the right-hand side, showcasing that we have anti-Markovnikov hydration and we have Markovnikov hydration, so we can get a ketone or we can get an aldehyde. On the internal alkyne, there is some stereochemistry I wanted to highlight. On the right-hand side, we showed that metal ammonia reduction gives a trans alkene, but hydrogenation with Lindlar's catalyst gives a cis alkene. I needed it to be an internal alkyne to highlight some of that stereochemistry because these two reactions give the exact same product on a terminal alkyne. Only internal will you see the cis or trans nature of those partial hydrogenations. We showed the full reduction. Then what's on the left-hand side should have been X2 addition, which is not regio-specific, but it is stereo-specific. It is an anti-addition mechanism. So when we do just one equivalence, we get anti-addition of the halogens, we get a trans alkene. The mistakes that I made, so what you're fixing by copying this all down, so cool to see you guys copying it all down again. What you're fixing is this and this. Those were drawn incorrectly before on the worksheet. And this one got cropped. My image cropped it. Oh, I mean, what am I doing? I'm posting on YouTube every day. Who cares if I'm in your phone? Okay. Who brought this one up last class? Yeah? Helpful? You see the fix now? Great. Absolutely. This doesn't need to be the only way that alkynes are introduced either. Um, I've told you guys before, you can make a table of reactions so that you can highlight the functional group change that each reaction provides. And even down here, we have more reactions with alkynes. If you wanted to, you could make one big reaction diagram where you put the alkyne in the middle and you show all 12 of the reactions, 5, 10, and then the radical reactions we had as well. You could make one big one with 12 arrows coming out of it, showing the 12 different ways that an alkyne can be changed. You can do the same thing with an alkene. We've got two reactions there, plus I want to say we had 12 reactions before that. Yeah, but I could be wrong on that. So if you're still looking for ways to familiarize yourself with all these different reactions, if you're looking for ways to spend time with it, make your own reaction diagrams. And maybe instead of separating them like I have, which I did on purpose, I separated them so that they are digestible and a little bit easier to see at a glance. Here's 12, and then we learned two more with alkenes. That gives you a total of 14 different reactions that you could put into one massive reaction coordinate diagram. And just the time spent making it helps you remember it more. All right, good? Great. Let's talk about the comparison of SN1 versus SN2 reactions. You guys still working on this? You want me to leave it up for a little bit more? Good? Okay. I want to substitute uh, an alkyl halide. And I want to make an ether. So I start with cis 1-bromo 4-methyl cyclohexane. Why is it cis? Both groups are on the same side. That compound, chiral, achiral, or meso? Raise your hand for meso. Achiral? Chiral? It's achiral. It lacks chirality. It has symmetry. I can draw a line of symmetry straight through those two carbons, and there's a plane of symmetry on either side. So those carbons are achiral. No chirality. But there is still stereochemistry. This is a cis stereoisomer because I could make a trans one, but they aren't chiral centers. Good. Let's say I want to start with this, and I want to make an isopropoxy. I'm going to name that for you guys. It's an isopropyl group connected off of an oxygen. That's how we name ethers. We just call it alkoxy. Whoops. Whatever the alkyl group is, plus the fact that it's bridged by an oxygen. And notice the stereochemistry. I want to preserve the stereochemistry. What type of reaction what type of substitution would allow me to preserve the stereochemistry? I do want to do substitution. Should I use a first order substitution, which results in a carbocation forming because the nucleophile is not weak enough to kick out the leaving group? Or should I do a second order substitution where the leaving group leaves because the nucleophile attacks the carbon and kicks out the leaving group? Why should I avoid SN2? Backside attack would invert the stereochemistry. What reagent would I use if I were going to do an SN2? What reagent would I use? Well, I want this oxygen with this carbon chain. And if I'm doing SN2, I would want it to be a strong nucleophile. So I give it that extra magnetic punch. Give it a negative charge. That would result in the backside attack. That would result in the inversion of stereochemistry. Not what I want. So instead, I want to weaken the strength of the nucleophile. I don't want it to come in like a strong magnet and get pulled right to that carbon and kick off the bromine. I want it to be a weak nucleophile that waits for the bromine to leave and then comes in to attack as a nucleophile. I want it to do SN1 to weaken its strength. I want that same carbon chain. I want the oxygen. I protonate it. I give it a proton. I introduce it as an alcohol instead of an alkoxide, excuse me. Instead of the negatively charged anion, I just introduce it as a neutral alcohol. Now it doesn't have the strength to attack the carbon, doesn't have that extra negative charge. Instead, it waits for the carbocation to form, and then it substitutes. Any issues that you guys see? It would need a deprotonation step, and that happens by the bromide, or it happens by another molecule of alcohol, but that happens after the substitution. It doesn't happen first, because there is no good base to deprotonate it. Yeah, you're right. I should clarify the temperature control to say that I'm promoting substitution and I'm not trying to get competition with elimination. But let's just say that we are looking for the elimination product. I can add low temp. I can add low temp to further clarify that I'm just doing substitution. Does SN1 always result in the retention of stereochemistry and that's it? SN2 always results in the inversion of stereochemistry and that's it? SN1 has the nucleophile attack a flat carbocation, which means either face of that carbon is open, and the nucleophile might add wedged, the nucleophile might add dashed, depending on how the nucleophile approaches the carbocation. I can get retention of stereochemistry and inversion of stereochemistry. So again, this question started by, what if I wanted to preserve stereochemistry? And the answer is, I can, but I'll get a mixture with inversion as well. Sure. If you're working in a lab, you want to synthesize this molecule only, you're going to have to do some chromatography. You guys remember chromatography from lab? What is it used as? like thin layer chromatography or column chromatography, what is their goal? Not weight, not mass. No, actually, mass is almost never a direct physical interaction. Mass is related to size, and size can be a direct physical interaction. But isomers all have the same mass, but if it's a longer chain isomer, it has much stronger interactions. If it's a more branched isomer, it has much weaker interactions. Chromatography is used for separation, purification. And these two chemicals are not the same as each other. They're very similar. They're diastereomers, but they are not the same. So I should be able to separate them using chromatography. So you said that's okay that I get both? Well, I don't know. What's the goal? Is this a new drug? Sometimes cancer drugs can result in diastereomeric mixtures or racemic mixtures when they're formed. One stereoisomer cures cancer or has good effects on cancer, and the other stereoisomer causes cancer. So, no, it's not good. You want to separate these before you send it to a patient. But some antidepressant medications are enantiomers. One enantiomer has the SSRL effect, the serotonin inhibitor, whatever, and the other has no effect. Not a negative effect, not a good effect, just no effect. So I wouldn't separate that one out at all. I would just synthesize it as easiest as possible and administer it because it's just going to weaken the dosage effectively. If you're talking about in this class, well, the point is to highlight the distinction between SN1 and SN2. The way that you can tell SN1 and SN2 apart is not just by the nucleophile and the substitution of the carbon, it's also by the change in chirality at a chiral center. It's not a racemic mixture. Good question. A racemic mixture has a specific definition. Nope. Yes. Racemic mixtures are a 50-50 mixture of enantiomers. And these are not enantiomers because achiral molecules don't have enantiomers. Achiral molecules can't have enantiomers. Achiral molecules have symmetry, and enantiomers, by definition, must lack symmetry in order to be non-superimposable with their mirror image. This would be a diastereomeric mixture. When racemic mixtures forms, when a reaction causes either one enantiomer or the other, racemic mixtures form 50-50 because those mirror images are exactly alike immediately before they form. So there can be no way for the reaction to control which one is favored over the other. They are exactly identical, and the statistics convince us that they're 50-50. Diastereomers, on the other hand, are not exactly the same as each other right before they form. They are not mirror images to each other. And so diastereomers rarely form 50-50. Enantiomers always form 50-50, giving us racemic mixtures. Diastereomers never form 50-50. So we don't have a cute little name for them, like racemic. By the way, racemic used to be the name of a carboxylic acid compound, racemic acid. And then Louis Pasteur realized that this racemic acid was crystallizing, and sometimes the crystals were growing clockwise, sometimes they were growing counterclockwise. And by hand, he separated these crystals, and then he found that they interacted with light equal and opposite ways. optical activity. And that idea of having enantiomers that were equal and opposite to each other stuck with racemic. So it became known as a racemic mixture. It stuck so well, they renamed racemic acid. They were like, that word now describes something applicable to all of chemistry, and so this compound has to lose its name so that we can steal it for something else. They now call it tartaric acid. No, most likely not, because they're not a racemic mixture. This is a diastereomeric, and diastereomeric mixtures are rarely 50-50. Distinction between SN1 and SN2. The type of the nucleophile, strong, weak, and the impact on chiral carbons, inversion, combination. All right, the impact or the distinction between E1 and E2 is a little similar. You guys okay if I erase this then? With E1 and E2, it's a little bicyclic structure. Yeah, I'm not going to lie. Most people wouldn't draw that bicyclic structure that way. Typically, we avoid drawing dashes to the rest of a structure, and instead, we infer the chirality or the stereochemistry by just drawing the hydrogens at that position. You guys might notice that those of you that have really big compounds that you're analyzing this semester, you've got these chiral carbons everywhere that the rings connect, bridgehead carbons. And rather than showing a wedge and a dash, usually it's just one group that is wedged or dashed. And you can infer the chirality, the stereochemistry from there. All right, I want to do a reaction on this bicyclic structure. I want to do an elimination. And I want to form oh, didn't mean to do that. I want to form an alkene that is tri-substituted. When it comes to bases doing elimination reactions, there are, I guess, a few different flavors of base. One flavor is Zaitsev bases. Zaitsev had a rule that said the most stable alkene will always form. And the most stable alkene is the most substituted alkene. If the least substituted or the less substituted alkene that could form does form, we call that an anti-Zaitsev alkene, and that requires an anti-Zaitsev base. And we only have one anti-Zaitsev base. That's tert butoxide. Tert butoxide does not form the most stable alkene. Instead, it follows the lowest energy barrier. But within Zaitsev alkenes, we have strong bases and weak bases. And strong bases that want to be Zaitsev can't always form the most substituted alkene. And that's because strong bases are stereochemically locked. They have to do elimination with an anti-beta hydrogen. Weak bases aren't controlled by stereospecific requirements. Weak bases are going to follow a carbocation intermediate and then act as a base. So weak bases can take any hydrogen from any position and form the most stable alkene. So within these three different flavors, we've got E2 bases, strong bases, anti-Zaitsev and Zaitsev, and then we've got weak bases that are always Zaitsev. Tert butoxide versus hydroxide or alkoxide versus water or alcohol. What type of base would be best for me to use here? I'm going to write that out a little bit better, sorry. But go ahead, tell me what you think. What type of base would do a good job here? Not a good job, sorry. The job. What type of base would get this job done? E2 requires that wherever the leaving group is, the beta hydrogen be antiplanar to it. Leaving group, alpha carbon, beta hydrogen has to be anti in order to be E2. If we spot the difference, if we look for what we're losing this hydrogen. That's the beta position that we're losing the hydrogen from. And that hydrogen, as we see down below, is not anti to the leaving group, which means an E2 mechanism cannot work. And this, to me, is, again, a confusing part about us trying to teach you the names of dead men as rules for chemistry. We say that strong small bases like hydroxide are Zaitsev bases, that they form the most stable alkene, but that is not true always because it requires that the Zaitsev alkene is antiplanar. So I don't like it. It's a little complicated, and that is okay. But you can't just slap a label on it and then think that it's always going to be the same. I cannot use an E2 base here because the E2 base will never take that red hydrogen. If I use tert butoxide is sterically hindered. Tert butoxide already wants to avoid a highly substituted area, and it wants to come towards a less substituted area to act as a base. So tert butoxide would run anti-Zaitsev elimination. But it turns out so would hydroxide. So would alkoxides. Because all of those are strong E2 bases, and they're never going to be allowed to take that red hydrogen. It might look like the anti-Zaitsev product, but it's the only E2 product possible. If I go to the right, I have to have a carbocation intermediate. That is the only way that I would be able to steal a hydrogen that is not anti, which means that I need to use a weak base, something that will not take a hydrogen until a carbocation has formed. In which case, I need something weak. I need water. I need methanol. I need ethanol. I need some type of weak base, some alcohol. And for those that are thinking it, yes, also heat to promote elimination so that we don't do substitution. What's the distinction between E1 and E2? There is a stereochemical implication. E2 is limited on what hydrogens it's allowed to get. And depending on the type of base running E2, there's a regiochemistry as well. E1 and E2 also differ by the type of base introduced. Things that are weaker magnets wait for the carbocations to form. Can I answer more questions about SN1 and SN2, E1 and E2? Me personally, I'm always anti-Zaitsev, never pro-Zaitsev. Good question. Technically, yes, because Zaitsev's rule was that the most stable alkene forms, and the one on top is the most stable alkene because it's the most substituted. But Zaitsev's rule is often taught as small, strong bases that run E2 go for the Zaitsev product. But we're seeing that these strong, small bases appear to be doing the anti-Zaitsev product. So, uh, yeah. The easy answer is the structure on the right is Zaitsev alkene. And I guess the clarification is that strong, small bases are usually Zaitsev. Oh, I guess there should be a third category. Usually Zaitsev if the stereochemistry allows. Okay. Maybe that's how I'll introduce it in the future. Thank you for helping me figure that out on the spot right now. Hmm. What's the substitution of this alkene? Di-substituted. Versus the Zaitsev alkene. Tri-substituted. Good. Okay. Let's see. We covered mechanisms enough, or you wanted to do more examples with mechanisms and arrow pushing? Yeah? Yeah. Yep. Britton, you make a good point, which reminds me, that's not the most Zaitsev product. That's just the second most Zaitsev product. All right, so let's do the mechanism here. Leaving group leaves, and I get my carbocation intermediate, which I think you were pointing out, Britton, the carbocation intermediate is adjacent to a tertiary carbon. So it should go through a hydride shift to form a more stable carbocation. You also asked this question at the end of class last time, which was the alpha carbon is where the carbocation will be or where the carbocation is. And I would say the alpha carbon is where the carbocation is. And if the carbocation rearranges, then the alpha carbon rearranges. The alpha carbon is like not a functional group. It's not a it's not a place. It's just us referencing a carbon of interest, and a carbocation is definitely a carbon of interest because things can add to a carbocation or pi bonds can form with a carbocation. So my alpha is rearranging, and now I have a tertiary alpha, and the most substituted alkene is actually not this one. The most substituted alkene would be this. What's the substitution there? Tetra. Are you guys confident on how to determine substitution of alkenes? Every semester I see it still trips people up. Here is a non-substituted alkene. It has no substituents. Well, it has no substituents, but it has no carbon groups either. I mean, to be fair, this is also a non-substituted alkene. Chlorines, alcohols, don't count as degrees of substitution. Monosubstituted alkene. I've got one carbon coming off of my alkene. My alkene makes up two carbons, and across both carbons of the alkene, there is one carbon group coming off. Tri-substituted alkene. I have one, two, three carbon groups coming off of my alkene. Tri-substituted, tri-substituted, di-substituted, tetra-substituted. What you can look for are the hydrogens that have been swapped out for a carbon. I mean, I say that because students in the past have said when they think about hydrogens should be attached to the alkene, and then I took that hydrogen to make space for a carbon bond. That seems to help them. But I would just look at the two carbons of your alkene and count how many groups coming off are carbon. 1, 2, 3, 4 tetra substituted. Mono substituted.
This, that terminal, when needs to be able to say all of that? Like, will there be questions about naming the structures? And if so, does that, like, is that part of nomenclature? Is it not going to be seen in nomenclature? Because I don't remember that, but at the same time, I'm like, is it mostly just helpful in knowing the, like recognizing that there are multiple, it's like that it's more substituted, right?
It's useful in understanding its regiochemistry. Yeah, mono, di, tri, and tetra substituted are regio descriptors. They are very similar to the methyl, primary, secondary, tertiary, quaternary that we had for carbons. But these regio descriptors describe alkenes as a whole, so you have to take into account both carbons.
One single carbon, and what is that one single carbon versus the two carbons that are formed in alkene?
Exactly.
And so it's not that we're going to be asked that terminology on the exam per se, but rather that it's going to be something that we just need to understand that that's what it means.
So it has come up before. I think in the same way that I could ask a question that says the alkyl halide in the molecule is a primary alkyl halide, secondary alkyl halide, tertiary alkyl halide. I could also say the alkene in the structure is a monosubstituted alkene, disubstituted alkene, trisubstituted alkene. True. Actually, your short answer questions are mechanisms and uh, the roadmap, filling in the reagents and filling in the structures. Your that's your only short answer stuff. The rest of your final is multiple choice. And I want to talk on that real quick, which the reason that I do multiple choice, because when I first started, I had zero multiple choice. Multiple choice questions are hard to write. I have to come up with 3 wrong answers, which actually is why a lot of my questions will say which of the following is not a possible solution, which of the following is not seen, because sometimes it's too hard to come up with 3 wrong answers, and it's a lot easier to come up with 1 wrong answer and 3 that are correct. When you tackle those types of multiple choice questions, I want you to rule out every single one. If you find a question that you think is correct, the other 3 should be easy enough to say they're wrong. Um, so even with nomenclature, you guys had to handwrite nomenclature on the midterm. That was part of your short answer work on the midterm. You are not writing nomenclature on the final unless it's a bonus question. Is that okay? Great.
Can you get like a similar question that might come up like with the exam? Just like as practice.
For SN1 and SN2,
Yeah.
E1 and E2? Yeah. And Vivi, what was your question? Yes, carbocation substitution is related to carbocation stability, but like not carbon substitution is this broad overarching idea, and carbocation stability falls into it. Is that your question? Yes. And they trend with each other. Stability increases with substitution. But then stability increases with resonance, regardless of the substitution. Like it starts over. A primary allylic system is more stable than a tertiary non-allylic system. Resonance, I mean, it should make sense. Remember I described a tertiary carbocation? It's got that positive charge, which of course is going to attract things to it, and it's very hard to form. If you shroud it with electron density, you've got all these carbon groups and all of their bonds and all of their electrons surrounding this carbocation, it makes it a lot easier to form. Where was I going with that? Oh, I call that moral support. Like they're helping to kind of protect or hide that positive charge. But what if instead of just moral support, I could literally take that charge and split it in half? Because now with resonance, my charge is not in one place or another. My charge is at 2 places, which means that it is half the charge it used to be. Sometimes with resonance, you get it in 3 or 4 places, and that stabilizes it even more. All right, so 2 ways that this could show up on the exam. One, your mechanisms. You'll have the choice between a substitution and an elimination mechanism. But that could be an SN1 or an E1 mechanism. That could be an SN2 or an E2 mechanism, and you get to choose. But I don't think that's what you're asking. I think you're asking how would identifying whether it's SN1 or SN2 show up, and that's going to be in the multiple choice. So we could see a question like this. This would be a hard one. I've put a question quite like this on the exam in the past. What reagent completes the reaction as shown? Sure. Or do you want me to add it back here? How come? What do you think it is? When it's not there, you think of a CH3. When it is there, you think of yourself? It's me. Hi, I'm the problem. It's me. You're welcome. It is kind of silly, right? Like we can represent a methyl group by drawing a line, or we can write in ME after we draw the line. I just want you guys familiar with some of the abbreviations we'll see sometimes. It's okay. One way you can tackle multiple choice questions is to say, one of these things is not like the others, and maybe that is the one that solves the problem. The trick is when you have a multiple choice question and none of the things are like each other, so they're all quite different. See a lot of cheat sheets in the room. I'm really proud to see that you guys have started them because that means you still have almost an entire week to recraft it and keep improving it and knowing what's on it before you get to the exam, which gives you a leg up. Okay, let's do another 10 seconds on this.
Okay, it's great for polymer
It depends on the polymers. Polyesters, you want to know a little bit more about esters, and that comes up in OCHEM too. Um, Polyvinyl chlorides or polyethylenes. Polyethylenes we could do right now. We have all of the chemistry we need for polymer chemistry with polyethylenes. You know, like HDPE, high density polyethylene. We could, I could make it make sense to you right now, but polyesters, you might want OCHEM 2. But that's just such a small part of OCHEM 2. You wouldn't need all of OCHEM 2 to be able to do polymer chemistry. Would I take OCHEM 2 over PChem? There's usually 2 semesters of PChem. Um, and one of the semesters of PChem was my favorite. Here's an initiator, a radical initiator, and it forms a bond with one carbon of ethylene, and that kicks off a chain reaction. I'm showing this as a mechanism as if all of the electrons are moving at once, but in reality, it would be form a radical, react, step after step after step. And so whatever your initiator is going to be connected to your chain, but eventually you just get a huge carbon chain. So you know it. You know polymer chemistry. I think I would have taken PChem over OChem 2, but boy, am I glad I was a chemistry major so I could take them all. What's your answer? Raise your hand for 1. Raise your hand for 2. Is that a hand? No. Raise your hand for 3. Raise your hand for 4. I only got 3 people that answered. You guys want to? Okay, now it's between 1 and 2. Raise your hand for 1. I think I added 2. You already had your hand raised for that one, right? I think I added 3 new ones. Raise your hand for 2. Okay, I think I added, I don't know. It's almost a tie. Okay, these are 2 very different reagents. Would you agree? One will take us through E1. So we should expect the most stable alkene will form. One will take us through E2. So we should expect the most substituted alkene should form, but it should be stereo specific, that the beta hydrogen will need to be antiplanar. This is not the most stable alkene. Can anyone tell me why? It's cis. It's a Z alkene. The high priority groups are on the same side. The trans alkene, its stereoisomer, is lower energy and is easier to form, which means E1 would prefer this product. So this must not have formed by E1. But why would E2 result in this? Is it clear that we need to take the beta hydrogen, the beta hydrogen needs to be removed from the tertiary carbon. And that hydrogen at the moment is or is not antiplanar to the leaving group. It is not antiplanar to the leaving group. But unlike the rings that we were dealing with before, this molecule has freedom of rotation. So if it rotates around the sigma bond, remember how we go from zigzag to zig-zig? The perception of this group from away now comes towards us. And now that beta hydrogen is anti to the leaving group. And so the alkene forms in this configuration. Nobody voted for tert butoxide. Anybody want to argue why? Good. Tert butoxide would have gone for the least substituted alkene, period. Nobody argued for cyanide. Any reason why? Cyanide is a strong nucleophile and a weak base. Cyanide would substitute that leaving group. It would not eliminate that leaving group. Cyanide would have given us this. I think that's great. You guys narrowed it down to the 2 most likely reagents, an E1 reagent and an E2 reagent. That is a very challenging question. I don't envision it being on the exam, but you wanted a version of what you could see on the exam, and that was a good push. See you Monday.
But it has to be able to go through a rotation.
I'm going to say no. E2 cannot happen if the beta hydrogen is not anti. E2 must have the beta hydrogen anti to the leaving group. If a molecule must rotate to make that happen, then so be it. If a molecule cannot rotate to have that happen, then it won't happen. Yeah, the wording was very close there. You see the distinction. Yeah, exactly. Exactly. If this was formed, this can't form from this alkene by E2. This stereoisomer cannot form, I said alkene. This stereoisomer alkene cannot form from this starting material by E2. It can by E1, absolutely, because E1 is not stereospecific. It's not stereoselective. Okay, Tanner.
So which one was it?
It's B. Yep. E1 would give the most stable alkene. And the most stable alkene would be the E alkene, not the Z alkene. Yeah? Mm-hmm. You want to see another one? This. Yeah, this forms with water. Because water is an E1 base. Yeah, E1 will always give the most stable alkene. Yeah, so it shows up as the most substituted and the least steric strain. If you remember when we talked about the stability of alkenes, we had mono-substituted, um, di-substituted cis, di-substituted trans, and then di-substituted terminal. And we said cis is less stable than trans because cis has that extra steric strain. And di-substituted was for a totally different reason. It's because of the resonance. Um, this has more protection of that more substituted carbon, more moral support, localized. Okay, one more question like this. All right, hang on. Hmm, I can't figure out what I want to do with this question. Hmm. Yeah. Oh, yeah, I know what I. Okay, sorry. Just pretend I didn't show you anything there. Which of these products does not form in this reaction? Quick. Means you know the relationship now. What do you got? Which one?
Third.
Third one?
No?
Mm-mm.
Oh,
What do you have? Yeah, but quietly. Okay. Should we do a raise of hands again? How many say one? Got six. How many say two? One. How many say three? Will not form. These are which product will not form in this reaction? Three, four. You're saying yes for four? Which of these will not form? If you're going to argue that two can form, then how can you argue that four won't? What's the difference between two and four? Just stereochemistry. They are enantiomers of each other. So if you form the ether at 2, how could you not also form the ether at 4? Especially since the ether at 2 preserves the stereochemistry and the ether at 4 converts it. No, I guess I said that wrong. If you were looking at 4 forming, then never mind. If you're going to get an ether as a predicted product, then you should only get an ether in the substitution product. There isn't a reaction that gives a combination of substitution that results in an ether and substitution that results in an alcohol. A reagent can either form an ether or it can form an alcohol, but a reagent cannot compete between forming an ether and an alcohol. And alcohols are precursors to what? To water. Alcohols are precursors to ethers. What is a precursor to an alcohol? Water. Water is a precursor to alcohol. Alcohol is a precursor to ethers. What type of alcohol do we have here? It is ethanol. I said that a little bit weird. What type of nucleophile do we have? What type of reagent? Strong base, weak base? Strong nucleophile, weak nucleophile? Weak nucleophile. So no temperature control noted. At a secondary carbon, a weak base, weak nucleophile is going to let a carbocation form. And once a carbocation forms, that weak nucleophile has no preference for doing elimination or doing substitution. It doesn't want to do either. It wants to go home and cook dinner and watch TV. But now that a carbocation has formed, it can take a hydrogen or it can bond to the carbon. And because the carbocation forms, it doesn't know whether it's attacking the carbocation from the top or attacking it from the bottom. This is an E1 SN1 competition, but it will never result in an alcohol because alcohols are precursors to ethers. Great.
You obviously said that this can't happen, but can you explain why the ethanol couldn't drop the H? Is it because it's part of the functional group? It's part of the alcohol? It's not. It
No,
would be all of it? Couldn't like protonate the ethanol and end up with or yeah, the H just wouldn't go from the, oh, yeah, that's fine.
So that's not a bad question. After the carbocation forms, oh God, I didn't think about my carbocation rearrangement again. Carbocations here would rearrange to the benzylic position. So actually just imagine that at each of these answers, I put that group at the benzylic spot instead. Luckily, that wasn't what the question was hitting at, but I missed that. Because the aromatic ring provides resonance at the benzylic position. It's something we get into more in OChem 2. So I didn't even... Oh, look at that. It's fixed now. Yay, it worked. I didn't need that. I didn't need that benzene ring. I was just doing it because sometimes I like to not just draw a carbon chain. I like to have have it look like an organic molecule. Okay, we formed this carbocation, and this is where ethanol acts as a nucleophile. I'm going to highlight these bonds. When ethanol acts as a nucleophile, it gets attached, wedged or dashed. And I think we can agree right now it doesn't matter whether it's wedged or dashed. The question is about why is it that the hydrogen is taken off and we're left with an ether rather than the carbon chain taken off? Okay. So the thought is that maybe my carbon-oxygen bond should break to the oxygen, which would leave me with my alcohol and a carbocation. Another way of showing that is this. A primary carbocation.
I think that I was thinking about the TS coming and attaching to the O, like in a different scenario. When, I don't even remember when it was. But it was the retro synthesis of
Okay.
like the O stays.
Here is an important idea. Which O is this in the end?
But the H, you know.
Yep. So that OTS leaves, that oxygen does leave. You're right. This O that's in the final product is not the same O. And that could come across as confusing. Why doesn't the TS leave and then the O just gets protonated?
Yeah. Like I figured it was probably the OH, which is why that's what I said. But I was just curious.
The opposite we can do. We can take the alcohol to the tosylate. But it's not as easy to take the tosylate to the alcohol. No, the question, which the wording was not written on the board, the question was, which of the following does not form in this reaction? One does not form because alcohols won't result in alcohols. Yeah, I could have added something like which does not, but that's, you guys have seen on the practice and on the midterm, I bold that stuff because I do it so often. Like one question will say, which of the following is bolded all caps seen in the IR spectrum? And then the following one is, which one is not? Because I don't want that to be the confusing part. You guys ever heard of this font that bolds certain letters or parts of words that make it easier to read as you scan across? It like takes advantage of your eyes' natural movements and pulls focus to certain parts of the words. It's like one of the more accessible font types, but I don't know exactly how it works. That's essentially what I'm trying to do manually, is draw your attention to the confusing part of the question so that you don't misunderstand it accidentally, because I'm not trying to test you on your reading comprehension. That shouldn't be the barrier here. I'm trying to test you on your chemical comprehension. Two and form, do form, two and four do form, because this is an SN1 E1 competition, and SN1 gives a mixture of stereo chemistries. Do you have a follow-up on that? Okay. Allie. Three forms. Three is the E1 product. And this results in a competition between SN1 and E1. Okay.
Um,
Correct. If I ran this with heat, I could promote just number three. If I ran this without heat, if I ran this at low temps, I could promote getting two and four. And you know what's strange? I mean, this is introductory organic chemistry. Most organic chemists are not doing reactions like this. They're using reagents that are massive, reagents that are themselves chiral, meaning that they interact with chiral starting materials in chiral ways, forming just one version of a chiral product. Um, so, like real organic chemists worry a lot about chirality, but they almost never worry about two and four forming. They don't worry about racemic mixtures because they control for that. But they would never know that a racemic mixture was even possible unless they took OChem 1. All right, shall we do a multi-step synthesis problem? And have you solved all of the multi-step synthesis that were on that last worksheet, or can I just use that worksheet?
you also like my, test the, or OTS, like things like that, where it's just like a bunch of letters, like less than, that are kind of fill in.
Yeah, and what's the question? Can I, oh, to the synthesis? Sure. Okay, I want to use the questions that I already wrote for that worksheet. So let's do number 2, which is show the formation of 2-butanol from 1,3-butadiene. This is organic synthesis and nomenclature in Unit 5. Has anyone solved this one already? No? One barrier in your way of solving this is nomenclature. You've got to be able to interpret those names to be able to figure out where you're starting and where you're ending. Buta, 4 carbons. Diene, one of them from 1 to 3, one of them from, sorry, one of them from 1 to 2, one of them from 3 to 4. And I want to make 2-butanol, 4 carbons, alcohol at the second position. Right? This one does not have any of the confusing letters, but I think the only confusing letter is OTS, right?
Like the MCPA. Like I don't.
Oh, okay. Yeah. I will say, I didn't teach you how to name epoxides, so I wouldn't. I I would only keep if I were to give you a multi-step synthesis that had just words, it would be compounds that you learned how to name this semester, so it would be limited to alkyl halides, alkenes, alkynes, and alcohols. All right, so we need to consume both double bonds. And we want to make sure that we do a hydration for one of the pi bonds being consumed and a hydrogenation for the other pi bond being consumed. Hydrogenation is where we'll add the two hydrogens across. It's important to remember, and I'll be honest, I don't know that we went over this a lot. Hydrogenation on polyalkenes doesn't stop at just one equivalence. If you have multiple alkenes in a compound and you run hydrogenation like you did in lab, all of the alkenes get hydrogenated. So if I start with H2 and PDC, I go from butadiene to butane. So I might want to get the hydration done first so that I still have alkenes to work with. But as it goes with most synthesis problems, there's usually more than one route. So hydration, I want the hydrogen on the less substituted carbon, and I want the alcohol on the more substituted. That's Markovnikov hydration. Anybody have reagents that I could use for Markovnikov hydration? H2O and H3O plus. Yep. There are multiple Markovnikov reactions. Oxymercuration reduction. Oxymercuration reduction is a Markovnikov addition as well. Either one of those would work well. And then are we close to the final product? No? What change do we need? That alkene needs to have hydrogens added across it. If I can take this from but 3-ene 2-ol, which is what I have now, but 3-ene 2-ol, and I want to get to butan 2-ol, 2-butanol, I just need to get rid of the alkene. And get rid of is a strange word. I need to add hydrogen across the alkene. I need to reduce the alkene to an alkane, and we have a reaction that takes alkene to alkane. What are the reagents? H2 and palladium over carbon. H2 with PDC. Done. Nice little multi-step synthesis. Right. H2 is in excess, and it's never written as if it's in excess, but H2, yeah, you can't provide it not in excess. Yes, the alkyne also goes directly to an alkane, or all the way to an alkane. There was another way that you could run this reaction. It takes more steps. What if I messed up and I hydrogenated my compound first? Come in. There's only one thing I can do with an alkane. Radical halogenation. And radical halogenation likes to go to the most substituted position. So I could put my halogen on that second carbon. It would go there preferentially, but that's not an alcohol. So how can I take an alkyl halide to an alcohol? NaOH, low temp, or H2O and low temp. Substitution. How do I make an alcohol? I use water or the conjugate base of water. Two different routes, one is longer than the other. Vivi. Mm-hmm. To be fair, radical halogenation is also a substitution. It's a radical substitution followed by an SN1 or an SN2 substitution. Yep. Okay, the other multi-step synthesis that I had was making 4-bromo-hexane 3-ol, hexane 4-bromo 3-ol from 3-hexyne. Did we do this one together? Yeah, okay, that sounds familiar. Oh, I see. And well, I'll just remind you, vicinal halohydrin indicates that you should try to use a alkene halohydrin addition at some point. 3-bromo-1-butene forming cis 4,5-dicyanocyclohexene. Cyclohexene, 1, 2, 3, 4, 5, cis dicyano. Do you know what reaction might be involved in that? The Diels-Alder is a 4+2 cycloaddition that leaves us with a cyclohexene and across from it 2 electron withdrawing groups. So in order to make this, I will need a conjugated diene. I'm almost at a conjugated diene and a dienophile. And the dienophile is always the 2 carbons that have these electron withdrawing groups. So how could I make a conjugated diene from my starting material? Elimination. I need to form a second alkene, so I definitely need to do elimination. What might be a good reagent for running elimination to form my conjugated diene? We have elimination reagents like strong bases that I could use. But if I want to do strictly elimination, and especially if one side versus the other doesn't really matter, regiochemistry, tert butoxide works as an incredible base because it doesn't really like to do substitution. I'm going to redraw my diene so that it's in its cis configuration. There's my S-cis conjugated diene. And I am almost at my final product. I just need to introduce the dienophile, which will be carbons 5 and 6 with an extra pi bond. And the 2 groups that they have in the final product are cis to each other. So in the reagent, they're also cis to each other. The stereochemistry of the Diels-Alder product tells you the stereochemistry of the Diels-Alder reagent. All right, Jordan, I recognize that did not use MCPBA, but I guess I should ask, do you know what MCPBA is used for? Is that that's why you wanted it specific, because you wanted to see it reviewed? When you said it just popped up. Oh, so you had it in a synthesis on your unit test, and you weren't sure what it did. Do you guys remember? Epoxidation of an alkene. Do you know what an epoxide is? Let's say that we start with 2-bromobutane, and we want to get to this final structure. There's your epoxide, Jordan, the structure on the right.
Is it specifically anything with that? The oxygen bonds for the two carbons?
Yes, an epoxide is a type of ether because it is ROR, and it's a type of ether where the two R groups are bonded to each other as well. So, but remember that an epoxide is not an ether because it has different chemical reactivity than ethers. So we give it its own name. Kind of like how not all OHs are the same. OH of an alcohol is different from the OH of a carboxylic acid. The ROR of an epoxide is different from the ROR of an ether, but the epoxide is that three-membered ring. 2 steps. If you see the epoxide, you should be able to work backwards to figure out what the epoxide formed from. Do you want to give its IUPAC name, Britton? The starting material of the epoxide? No, you had it right the first time. 1-butene. The alkene will have to be the same 2 carbons of the epoxide. 1-butene. And the reagent to take a peroxide, an alkene to an epoxide is any type of peroxy acid. MCPBA is just a specific type of peroxy acid. A peroxy acid, peroxy means extra oxygen. And so it's not a carboxylic acid, it's a carboxylic acid with an extra oxygen. It's a peroxy acid. And it's that extra oxygen that gets dropped onto the alkene to form the epoxide. So I need to form that alkene. What type of reaction is needed there? Elimination. And what reagent can I use to run that elimination? Only tert butoxide in this case, because if I tried something like sodium hydroxide and heat, or sodium methoxide and heat, or water and heat, or ethanol and heat, I'm always going to get the Zaitsev alkene. I'm always going to go to the more substituted alkene. Here, I need specifically the less substituted alkene, so I need to use my anti-Zaitsev bulky base, tert butoxide. Thank you guys for your time. Head over to Johnny if you want to do more practice stuff. Come tomorrow night, 6 to 8 upstairs, other wing, 354 for another review session. Monday, what time do we meet? 5:50, we start the exam. I'll try to be in here around 5:40, 5:30 or 5:40. And where? Right here. Okay, see you guys Monday night. Happy studying.